Today we are going to see the next topic, that is forces in space. Now what do you mean by forces in space? We have already learned about forces in 2 dimensions, right? So forces in space means forces lying in 3-dimensional space. Okay, so these forces are also known as space forces. To begin with, we will be concentrating on how to find the resultant of number of forces in the space. So after that, we will see all the equilibrium equations available for solving the problems related to space forces, and then we will see how to find the moment of a force about a point. Now let's start with forces in space. Now this figure shows the space diagram. So here you can see 3 axes, x-axis, y-axis and z-axis. Now if you want to represent a point in the space, we need minimum 3 coordinates. The x-coordinate, y-coordinate and the z-coordinate. So let us consider 2 points in space, A and B. Okay. And also let x1, y1, z1 represent the first point and x2, y2, z2 represents the second point. Now let us assume that the force of magnitude capital F is passing through these points. Okay, and this shows the line of action of the force. You can see that the line of action is passing along these 2 points. Now we have already learned how to find the resultant of inclined forces lying in the 2D plane. What we did was we resolved all the inclined forces along 2 directions. One along the horizontal direction and one component along the vertical direction. Then we found out the algebraic sum of all the forces lying in the horizontal components. Similarly, we found out all the vertical components, algebraic sum of all the vertical components. And finally, we found out the resultant using the equation R is equal to square root of sigma v square plus sigma h square, where sigma v is the algebraic sum of all the vertical forces and sigma h was the algebraic sum of all the horizontal forces. So this was the method, or this was the steps followed for finding out the resultant force lying in the 2D plane. In order to find the resultant of all the forces lying in the 3D plane, we will follow the same steps that we have followed for finding out the resultant of forces lying in the 2D plane. But the only difference is we need to resolve all the forces along 3 directions. Along the x direction, along the y direction and along the z direction. That is the only difference. So here you can see that capital F is an inclined force. So here we can resolve this force into 3 components. Component along the x direction, component along the y direction, and component along the z direction. Let Fx denotes the component of the force acting along the x-axis, Fy denotes the component of force acting along the y direction, and Fz denotes the component of the force acting along the z direction. Now let us see how we can represent a force in space in the vector form. So this is the formula for representing the force in the vector form. That is, force in vector form is equal to F dot lambda AB, where this F is the magnitude of the force given in the question and lambda AB is the unit vector for AB through which the force is acting. Okay, lambda AB is the unit vector for AB. Now, how will you find out the unit vector? That can be obtained using this formula. That is x2 minus x1 into y plus y2 minus y1 into j plus z2 minus z1 into k divided by square root of x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square. So using this formula, you can find out the unit vector. Now here x1, x2, y1, y2, z1, z2 are the coordinates of the point A and B. Okay. Now here one point is very important and that is to be kept in mind. In our case, A is the originating point and B is the final point. So while finding out the difference of coordinates, we must subtract the coordinate of the originating point from the final point. That means when you find out the difference of coordinates, we will be subtracting x1 from x2, y1 from y2 and z1 from z2. This is very, very important. Now, if we are subtracting the coordinates of the final point from the originating point, that is x1 minus x2, y1 minus y2, z1 minus z2, then the direction of the force will get reversed. So, instead of acting in this direction, this force will be acting in the opposite direction. Hope you understood that point. So, this is very, very important. You have to keep that in mind. Okay, so when you find out the unit vector, you have to consider the direction of the force also. Now let us consider another case. Instead of the points through which the force acts, just assume that we are given the angles made by the force with respect to x, y and z axis. So in that case, how we can write the force in the vector form? That can be done using this formula, that is f in the vector form is equal to f cos theta x into y plus f cos theta y into j plus f cos theta z into k, where theta x is the angle made by this force with respect to the x axis, theta y is the angle made by the force with respect to y axis, and theta z is the angle made by this force with the z axis. Or this equation can be written as f in the vector form is equal to fx into y plus fy into j plus fz into k. Now what is fx? Fx is equal to f cos theta x. This fy is equal to f cos theta y, and fz is equal to f cos theta z. Now if we want to find out the magnitude of the force, that can be found out using the equation f is equal to square root of fx square plus fy square plus fz square. Now again we know fx is equal to f cos theta x, right? So from this equation you can find out what is cos theta x or what is theta x. How will you find out that? Cos theta x is equal to fx by f, or theta x will be equal to cos inverse of fx by f. That will give the direction of the force capital F with respect to x axis. Similarly, you can find out cos theta y, which will be equal to fy by f, or theta y will be equal to cos inverse of fy by f, and cos theta z is equal to fz by f, or theta z will be equal to cos inverse of fz by f. Now, there is one more identity that is very important. That is cos square theta x plus cos square theta y plus cos square theta z is equal to 1. This is one of the very important identity which has to be remembered. In some problems, sometimes one angle may not be given. In such cases, we need this identity to find out the unknown angle. So, now we have learned how to write the force in the vector form if the coordinates of 2 points along which the force passes are given, or if the angles made by the force with respect to x, y and z axis are given. Now, we will see how to find the moment of a force. So, in general, how will you find out the moment of a force? Yes, we will multiply the force with the perpendicular distance between the line of action of the force and the point about which we need to find the moment. In the three-dimensional case, what we need to do is first find the force vector, then obtain the position vector of 2 points. What are those 2 points? The first one is the point about which we need to find out the moment, which is also known as the moment center, and the second one can be any point lying on the line of action of the force. Let us consider 2 points A and B. The coordinates of point A are x1, y1, z1, and the coordinates of point B are x2, y2 and z2. Let a force of magnitude capital F passes through these 2 points. So the line of action of the force passes through the points A and B. Now consider another point C whose coordinates are x3, y3 and z3, about which we need to find the moment of this force. Okay, so as I have told earlier, the first step is to write the force in the vector form. So we know how to write the force in the vector form, right? So what is the formula? So F in the vector form is equal to dot product of the magnitude of the force and the unit vector of A and B, right? So you know how to find out the unit vector lambda AB also. Okay. Now, what about the second step? Second step is to find out the position vector of 2 points. So, what are the 2 points to be selected? The first one is the moment center and the second one can be any point lying on the line of action of the force. So, it can be point A or it can be point B or it can be any point lying on this line of action. But in our case, we know the coordinates of only 2 points, that is point A and point B. So, the second point can be either point A or you can take point B. So, let us take point A. So, we need to find the position vector CA. So, in our case, C will be the originating point and A will be the final point. So, we need to find the position vector RCA. So, how will you find out the position vector RCA? That will be equal to x1 minus x3 into I plus y1 minus y3 into j plus z1 minus z3 into k. So, this is the position vector RCA. You have to be very careful. You have to take the originating point as the moment center and the final point will be any point lying on the line of action of the force. So, when you find the position vector, you have to subtract the coordinates of the originating point from the final point. That is x1 minus x3, y1 minus y3 and z1 minus z3. Clear? Okay. Now, the next step is to find the moment. Moment of the force capital F about the point C. So, we will be obtaining the moment in the vector form. So, how will you find out the moment? So, that can be found out using this formula. That is, moment of the force about the point C in the vector form will be equal to the cross product of the position vector RCA and the force vector. This can be written like this: IJK XYZ Fx Fy Fz. So in our case, what is x? X will be x1 minus x3. So what is y? Y will be y1 minus y3 and z will be equal to z1 minus z3. Now Fx, Fy and Fz are the force components along the x, y and z direction. This is again equal to I into yfz minus z into fy minus j into x fz minus zfx plus k into x fy minus y fx. So, this is how we will be finding out the moment of the force F about the point C. Now, let's see how to find the resultant of forces. So, if there are a number of forces acting in space, what is the first step? You need to resolve all the forces into 3 components. That is, along the x direction, along the y direction and along the z direction. Then you find the algebraic sum of all the forces in the x direction. So that will be denoted by Rx. Okay. So what is Rx? Rx will be equal to algebraic sum of all the forces in the horizontal direction or all the forces along the x direction. Similarly, you can find out Ry. What is Ry? You find the algebraic sum of all the forces along the y direction. So, there is Ry. And similarly, you find out what is Rz. Rz will be algebraic sum of all the forces along the z direction. So, finally, you can find out the resultant R using the equation R is equal to square root of Rx square plus Ry square plus Rz square. Now let's see what are the equilibrium conditions available. Now for equilibrium, the resultant force acting on the system must be equal to 0. So that means sigma fx must be equal to 0, sigma fy must be equal to 0, and sigma fz also must be equal to 0. Then we have three more equations, that is sigma mx equal to 0, sigma my equal to 0, and sigma mz equal to 0.